I tried to convince you in the Zoom today that there's a better number system than base 10. Base 10 was arbitrary based on our biology. I think that's something we probably mentioned earlier in the year, but base 10 is based on the fact that we have 10 fingers and people counted on their fingers. And so people always used measurements in dozens. A lot of trade was done in dozens or dozens of dozens. A dozen is a gross 144 of something. And the reason things have been sold in dozens for so long is because they're more easily divided. A dozen can be evenly divided by many more factors than 10. We'll get to that later. But I would have shown this short video in the Zoom, so I'm going to show it here. And you'll begin to start to see the advantages of a base 12, which is called a dozenal. That's not surprising, the word dozen is right in it. Or duodecimal. We know deci means 10. Duo is 2, so 2 and 10, 12. A duodecimal or a base 12 system.
Math is fine, but it can be better. If nature could choose between building things with squares or triangles, it would choose triangles, because triangles are stronger structures. When we take a square and a triangle and apply forces to them, a square will slant and buckle, but a triangle will hold strong, and that's why we use triangles to build bridges. The triangle is the most basic shape, 3 sides and 3 corners. We see 3 and multiples of 3 popping up in nature all the time. Let's look at something as simple as a circle, for example. If we want to pack a bunch of circles together in the most efficient way possible, we would do it like this. 1 in the middle, surrounded by 6. You couldn't pack them closer if you wanted to. This is how a grocer would pack oranges. Now if we connect the center of the circle with straight lines, we see a hexagonal pattern emerge. And this pattern is used by nature in beehives. It's the most efficient way to use space. Nature wants to talk in 3s. Now when we look at our math system today, we use something called the decimal system. The decimal system is groupings of 10. If we want to use math to solve problems found in nature, then by using the decimal system, we're just making it hard on ourselves. The natural grouping of things is 3s, and 10 does not divide by 3 very well. In fact, 10 doesn't divide well by much at all. Say you had 10 oranges, and you were bringing them home to your kids and told them to divide them equally amongst themselves. If you had 2 kids, it would be fine, or 5 kids, it would be fine. But if you had 3 or 4 or 6 kids, they would start arguing about who should get more, and let's face it, you were just giving them oranges to shut them up for a while. Now let's say you had 12 oranges. If you wanted to divide them up amongst kids evenly, you could have 2, 3, 4, or 6 kids, and everything would be fine. Using 12 as a grouping order is better, and this system is called the dozenal system. It makes everyday maths easier and makes arithmetic a more enjoyable learning experience. 12 and 3 are best friends. The decimal system and the world we live in are not. Start counting in 12s. A counting system based on 3s makes life easier. Don't you agree?
Now you've grown up using base 10. So it's what you're familiar with. So this system is going to seem hard, but that's just because you've been learning using a different base number all your life. People knew that 12 was a great number to use when they came up with measurements. There are 12 inches in a foot. Things are sold in dozens. 12 hours is half a day. 24 hours in a day, that's 2 12s. 60 seconds in a minute, 60 minutes in an hour, all multiples of 12. The fact that 12 can be divided up in so many ways was known for a long time, and that's why so many measurements were based on 12 or multiples of 12, because people needed to trade things and divide things up. And what ended up happening was, because we had this arbitrary decision based on 10 fingers, we tried to fit our measurement system to match our bad choice of number system. And there you have the metric system. And the metric system is easier to use and to understand if you're stuck with a base 10 system of numbers. If we had, instead of adopting the metric system, if we had shifted to a base 12 number system, that would have made math and trade and commerce and so many things much easier. Of course, you were talking about a generational shift that would not have been easy to do, or to get it started at least. Here's a little, back in 1973, Schoolhouse Rock did a little explanation of base 12 called Little 12 Toes.
Now, if man had been born with 6 fingers on each hand, he'd also have 12 toes, or so the theory goes. Well, with 12 fingers, he probably would have invented 2 more digits when he invented his number system. Then, if he'd saved the 0 for the end, he could count and multiply by 12s just as easy as you and I do by 10s. Now, if man had been born with 6 fingers on each hand, he'd probably count 1, 2, 3, 4, 5, 6, 7, 8, 9, dec, el, do. Dec and el being 2 entirely new signs meaning 10 and 11, single digits. And his 12, do, would have been written 1, 0. Get it? That'd be swell to multiply by 12. Hey, little 12 toes, I hope you're well. Must be some far-flung planet where you dwell. If we were together, you could be my cousin. Down here we call them a dozen. Hey, little 12 toes, please come back home.
Okay, so every time I show that, I'm laughing to myself because every time I show that in class, so many students think it's creepy. I don't know what it is, but it's from a long time ago, obviously, right? We're talking about almost 50 years ago, but that Schoolhouse Rock thing was a thing. You probably heard conjunction junction. I guess the reason I like to still show it is because it opens up this idea that, you know, when we looked at binary base 2, we only had 2 symbols, 0 and 1. Just like with base 10, we have 10 symbols, but one of them is the 0. So if you have 12 symbols, you can go ahead with your 0 through 9. There's 10 of them, but you need 2 more. You need a symbol for 10, a single digit. 10 all of a sudden becomes a single digit in a base 12 system, as does 11. And so you need symbols to represent that single digit value. And so it makes sense that you would use X for 10, sort of think about Roman numerals, and then E, capital E for 11. And there you go, you've got your 12 symbols. But, you know, we said that and it's true that base 10 was arbitrary based on our biology, but you could still count to 12 on your fingers. And if I start talking too soon, you're still thinking about it, just pause the video and then restart when you're ready. Sometimes students say count to 5 and then count your palm as 6. So you could go 1, 2, 3, 4, 5, 6 and then 6 more on the other hand, or count your arm as the 6th digit. An even easier way is if you look carefully, if you ignore your thumb and look carefully at your fingers, each of your 4 fingers has 3 sections. And so you could still count on your fingers just by counting the sections. 1, 2, 3, 4, 5, 6, 7, 8, 9, dec, el, do. So when you get to do, you're at 12. And you could even keep track of the 12s on the other hand. So I've got 1 12, okay? 13, 14, 15. You could go as many 12s as you would go as many as 12 12s just on your 2 hands and keep track of how many 12s you have on your second hand. And go up to 144. You could count all the way up to 144, which is a gross. Although in base 12, it would look like 100. 1 12 squared plus 0 12s plus 0 1s.